Okay, in this class we'll discuss some of the important problems which is based on the fatigue load subjected to combined loading. Okay, first let us understand the given problem. Okay, so the problem is a steel cantilever member as shown in this figure. Okay, this is a steel cantilever member, okay, which is subjected to a transverse load, okay, as it end that varies from 450 newtons, okay, 450 newtons upward, 45 newtons, okay, 45 newtons upwards, okay, to 135 newtons downwards, okay, which is 45 newtons upwards and 135 newtons downwards, okay. As an axial load varies from 110 newton, okay, and as an axial load varies from 110 newton, okay, 110 newton compression, okay, which is acting this side compression, to 450 newton, okay, 450 newton in tension, okay, 450 newton, you can see this is the 450 newton in tension, okay. So what is that load? An axial load varies from 410 newton compression to 450 newton tension, okay. Here what we need to do, we need to determine the required diameter at the change in cross section. This we need to find out here, okay, change in cross section for infinite life. Here we need to find out the required diameter at the change in cross section, okay. This is the change in cross section of this steel cantilever beam, okay. So here we need to find out the value for d, okay, we need to find out the value for d, okay, for infinite life using the factor of safety of 2, okay. The strength properties of the material as ultimate strength they have given 550 MPa, yield stress they have given 470 MPa, and endurance limit they have given, okay, 275 MPa, and small q notch sensitivity factor they have given which is 1, okay, which is 1, okay. This is a given problem, okay. Here what we need to find out, we need to find out the diameter small d, okay, at change in cross section of the steel cantilever beam, change in cross section of the steel cantilever beam, okay. This is a given problem. Here first let us note down the given data. As we all know that, okay, sigma u is equal to 550 MPa, okay, sigma y is equal to 470 MPa, and sigma minus 1 is equal to 275 MPa, and q is equal to 1, okay, it is a notch sensitivity. FOS, which is n is equal to 2, okay. Here they have given two conditions here, okay. First it is subjected to bending, and one more it is subjected to, okay, axial load, okay. For example, if you go for an axial load, okay, F maximum is equal to, okay, which is F maximum with respect to tensile, which is 450 Newton, okay. What is the F minimum here with respect to this problem, which is minus 110 Newton, okay, which is subjected to an axial load, for axial load, okay. Same way if you go for bending, here we have upwards 45, downwards, okay, we have downwards we have 135, okay. For example, here F maximum, which is 135 Newton, F minimum is equal to minus 40 Newton, okay, which is for bending, okay. So this is the given data, okay, this is a given data with respect to this problem. Here for combined load condition, what is the equation we have, we already discussed, okay. So in this previous class, so sigma equivalent is equal to, for example, if, okay, the member is subjected to variable load, okay, bending moment and variable axial load, at the time we need to consider these equations, okay. Sigma E max or sigma E is equal to equivalent, okay, sigma equivalent axial plus sigma equivalent bending we need to consider, okay. With respect to these equations we need to follow, okay, which is equation number 5.65 as well as 5.61 from the design data handbook, okay. If the, okay, the steel cantilever beam here which is subjected to, okay, variable bending as well as variable axial load condition, okay. So at the time we need to consider this equation. Okay, now for combined load formula is sigma E is equal to sigma max is equal to sigma equivalent axial plus sigma equivalent bending. Okay, sigma equivalent axial plus sigma equivalent bending. Okay, so this is what we need to find out. Okay, this is the equation. First condition, first we will go with an axial load. For example, we have an axial load, okay, which is for axial load condition, for axial load sigma equivalent axial is equal to sigma MA plus sigma SD divided by sigma minus 1D into sigma A into K sigma minus 1. Okay, so which is equation number 5.65. Equation number 5.65 from the design data handbook. Okay, next what we need to find out? Okay, first we need to find out sigma MA. So each and every term we need to find out with respect to this equation. First let us find out sigma MA. Sigma MA is equal to, what is the equation? FM divided by A. Okay, area. What is where FM is equal to F maximum plus F minimum divided by 2. Okay, so that is equal to, if you substitute that value, okay, what is the F maximum, which is 450. What is that F minimum? Okay, which is minus 110. Okay, here again minus into plus. Okay, it will become minus 110 divided by 2. We will get 170 Newton. Okay, so that is the FM. Okay, what is the, now if you substitute these values into this equation, sigma MA is equal to, what is the FM? Okay, which is 170. What is the area of this okay, the steel cantilever member? Okay, which is pi d square divided by 4. Okay, if you substitute this, okay, if you simplify this, we'll get 216.45 d square respect to d only, Newton per mm square. Okay, sigma MA is equal to 216.45 divided by d square, Newton per mm square. Okay, so this is the sigma MA with respect to d only. Okay, now next what we need to find out? Okay, we need to find out sigma A. Sigma A is equal to, what is the equation? Okay, with respect to this stress amplitude, okay, FA divided by A. What is the formula for FA? FA is equal to F max minimum, F max minus F minimum divided by 2. See, we are talking with respect to this axial load only. Okay, now if you substitute that value, what is the F max? Okay, 450. Okay, here already we have minus into minus, we get plus, which is 110 F minimum divided by 2. Okay, so we'll get 280. Okay, newtons. 280 newtons. Okay, if you substitute that values, okay, if you substitute that value, this value into this equation, sigma A is equal to 280 divided by 5 by 4 pi d square divided by 4. If you simplify this, we'll get sigma A is equal to 356.5 divided by d square in terms of Newton per mm square. Okay, in terms of Newton per mm square. Okay, this is the sigma A with respect to this equation. Okay, next what we need to find out? we need to find out sigma SD. Okay, sigma SD, this value. Okay, sigma SD is equal to, okay, sigma y divided by n. Okay, so we know the sigma y which is given in the problem, yield stress, which is 470 divided by 2, which is 235 Newton per mm square. 235 Newton per mm square. Next, what we need to find out? Sigma 1 minus d. Sigma 1 minus d is equal to sigma minus 1 endurance limit ESZ ESR EL divided by n, the factor of safety. Okay, sigma minus 1d is equal to endurance limit ESZ ESR EL divided by n. Okay, which is factor of safety. How to find out these things? Okay, with respect to this problem. Okay, as we all know that already we solved n number of, okay, 1 or 2 problems based on these conditions. Okay, now you can observe here, assume, okay, so if it is an axial load, okay, if the diameter of the shaft, okay, whatever it may be conditions, okay, assume the size factor ESZ is equal to, size factors ESZ is equal to 0.8. okay, if it is 7.5 less than d or less than or equal to 50, less than or equal to 50. okay, for sigma u is equal to 550 MPa, sigma u is equal to 550 MPa. okay, sigma u is equal to 550 MPa from figure 5.3 in design data handbook. Figure number 5.3 in design data handbook. Okay, I will show you how to find out that, okay, the surface correction factor, okay, with respect to ultimate stresses which are given in the problem. Okay, now you can see, okay, this is a figure number 5.3. okay, from the page number 5.8 from the design data handbook. Okay, so reciprocals of stress concentration factor caused by surface conditions. Okay, so if it is a rough surface, okay, for that we need to find out the ESR. okay, for that we have ultimate strength of 550 MPa. okay, somewhere here we will get 550. okay, if you draw one straight line, okay, if you draw one straight line up to here, okay, up to rough surface, where exactly which is coincide this rough surface line, from there you draw one more line. okay, from there you draw one more line which is okay, intersect this particular line. okay, from there, okay, you will get the surface factor. okay, surface factor we already solved. I have already shown that how to measure that value, okay, by using proper instruments. okay, so from design data handbook, okay, which is figure number, okay, 5.3, here we have the rough surface, okay, so for that what you need to do, okay, we have ultimate stress of 550 MPa, okay, that is sigma u. okay, here ESR, in x axis we have ultimate stress, y axis we have, okay, the surface condition. okay, so for that you draw one line like this, okay, where exactly which is intersect this rough surface line. From there you draw one more line, okay, so which is okay, which is parallel to this line. okay, somewhere here we'll get 0.83. okay, this is how we can find out the ESR with respect to this. okay, ESR is equal to 0.83. next, EL for axial load. okay, we discussed in the last problem also. okay, we need to assume 0.7 for axial load, 0.7 for the axial load. okay, next, if you substitute all the values into this equation, okay, into that if you substitute all the values into that equation, sigma minus 1d is equal to, what is that endurance limit we have? 275. Okay, 275 into 0.85 into 0.83 into, okay, 0.7 divided by, okay, the factor of safety which is given in the problem, which is 2. If you simplify this, sigma minus 1d is equal to 67.904 Newton per mm square. 67.904 Newton per mm square. Newton per mm square. Okay, so next what we need to do, we need to find out the stress concentration factors. Okay, for that given equation, stress concentration factor, we need to find out that K sigma minus 1. Okay, we know the notch sensitivity. Okay, from the figure d by d as well as r by d ratio, we can find out this. Okay, the stress concentration factor. Okay, we'll see that to find K sigma minus 1 from figure 4.20a from the design data handbook for d by d is equal to 2d divided by d 2. Okay, do d get cancel? Okay, dd get cancel. Okay, same way r by d ratio, r by d is equal to, what is the r? Okay, which is 0.2 times of d divided by d, dd get cancel, which is will get 0.2. Okay, from figure number 4.20, okay, in x axis we have r by d ratio. Okay, in x axis we have r by d ratio, in y axis we have k sigma. Okay, y axis we have k sigma. Okay, if you okay, by using this r by d, d by d, okay, here we have d by d. Okay, d by d lines, d by d which is equal to 2. Okay, here we'll get r by d is equal to 0.2. Okay, if you draw one line, okay, up to here where which is exactly coincide this d by d line. Okay, from there you draw one more line. Okay, somewhere here you'll get 1.635. this is the stress concentration factor. Okay, this is the stress concentration factor. K sigma is equal to 1.635. next we need to find out this K, okay, sigma minus 1, K sigma minus 1. For that we have a equation, okay, that is K sigma minus 1 is equal to 1 plus Q into K sigma minus 1. This is the equation. Here we know that, okay, where Q is equal to 1, okay, the notch sensitivity factor. Okay, so here if you substitute all the values into this equation, okay, so the Q which is given in the problem, okay, if you substitute 1 plus 1 into K sigma, 1.635 minus 1, okay, if you simplify this, K sigma minus 1 is equal to, you'll get 1.635. okay, you'll get same value. Here what happened, okay, the K sigma is equal to K sigma minus 1. K sigma is equal to K sigma minus 1. If you simplify this, we'll get K sigma minus 1 is equal to 1.635. okay, same thing, 1.635. here this will become this, K sigma is equal to K sigma minus 1. okay, same value will get. Then by using all these values, okay, if you substitute, okay, if you substitute all the values into that equation number 1, okay, if you substitute all the values into that equation number 1 or equation number 5.65, okay, so that is equation, okay, sigma equivalent axial is equal to, okay, sigma ma plus sigma sd divided by sigma minus 1d into sigma a K sigma minus 1. okay, substitute all the values into this equation. What is the sigma ma? With respect to d only, 216.45 divided by d square plus 235 sigma SD 235 divided by, okay, 67.904 into sigma A with respect to D only, okay, we'll get 356.507 divided by D square into 1 point, okay, what is the stress concentration factor? Will get 1.635. 1.635. If you simplify this, we'll get, okay, 2233.683 divided by D square Newton per mm square. Okay, next we have one more condition, okay, which is the second condition for bending load. Okay, for bending load, okay, for bending load, what we need to do? Second condition, for bending load, this is a for bending load. You can see here sigma equivalent, bending equivalent, that is the equation is sigma mb plus sigma sd divided by sigma minus 1d, okay, into sigma ba into k sigma minus 1, k sigma minus 1. Okay, here what we need to find out? Sigma mba first, okay, sigma ba, you find out sigma ba, okay, what is the formula? mba divided by zb, okay. So here we know that maximum bending moment, okay, which is given in the problem, okay. So here mb max, what is that? mb max minus, okay, mba is equal to mb max minus mb minimum divided by 2, mb minimum divided by 2, okay. So what is the mb max, mb minimum? If you substitute that all the values, before that you find out maximum bending moment with respect to this 45, okay, with respect to this reduction which is 125 at what low or what, okay, the bending moment at what distance, okay, at 125 mm, okay. Now if you substitute that values, mb max is equal to 135 into 125, okay, you will get 16875 Newton mm, okay. mb minimum is equal to minus 45 into 125, okay, you will get minus 5625 Newton mm, 5625 Newton, minus 5625 minus 45 into 125 will get minus 5625 Newton mm, okay. Same way what we need to do, we need to substitute these values into this equation, okay. Now what is that mb maximum? Will get, okay, 16875 minus into minus, okay. So here minus into however much you get 5625, okay, divided by 2, okay. If you simplify that, we'll get 11250 Newton millimeter, which is MBA, okay. If you substitute this value into this equation, okay, this value into this equation, now you can see here, okay, now you can see that 11250 divided by what is this? ZB, okay. So which is 5d cube divided by 32, okay. If you simplify this, we'll get sigma BA is equal to 114.592 into 10 to the power 3, okay, 114.592 into 10 to the power 3 divided by, okay, divided by d cube, divided by d cube. Okay, this is the value with respect to this sigma BA. Next, what we need to do? We need to find out the sigma, okay, BM. Sigma BM is equal to, what is the formula? Sigma BM is equal to MB M divided by ZB. Okay, MBM divided by ZB. Okay, same thing. What is that? MBM. MBM. Okay, so MBM is equal to MB max. MB max plus MB minimum divided by 2. Okay, if you substitute that values into this equation, 16875 plus into minus 5625 divided by 2 will get 5625 Newton millimeter. Okay, if we substitute this value into this equation, we'll get 5625 divided by pi d cube divided by 32. Okay, if we simplify this, we'll get 57.296 into 10 to the power 3 divided by, okay, d cube. Okay, this is a value. Okay, now, okay, sigma SD is equal to, we already find out that, okay, for the axial load, which is 235 Newton per mm square. Okay, 235 Newton per mm square, which is same as axial load, because the yield stress, okay, which is sigma y by, okay, this one, the factor of safety n, right? Okay, which is, will get same value. Okay, so from that we can find out that, okay, sigma y will get same thing. Okay, so this is the sigma st is equal to sigma y by n will get same value, okay, as that of axial load. Okay, as that of axial load. Next, what we need to find out? Sigma minus 1d. Sigma minus 1d is equal to, okay, sigma minus 1 into ESZ ESR EL divided by n. Okay, here EL is equal to 1 for the bending load, as we all know that we need to assume EL is equal to 1 for bending load. If we substitute this value into this equation, we know that endurance limit which is given in the problem, which is 275 into 0.85 into correction factor same as that of axial load, that is 0.83 into 1, okay, divided by 2. If you simplify this, okay, we'll get 97 Newton per mm square. 97 Newton per mm square. This is the sigma minus 1d. Okay, with respect to that equation number 1,